Today is, as per your request, a bit more of a technical note here on the fundamentals of mixture design specific for 3D concrete printing. So as I mentioned in the previous presentation, 3D concrete printing is a form of additive manufacturing used to fabricate buildings or construction components with completely new shapes previously impossible with traditional formwork. However, if you want to be able to fabricate these new buildings and these new shapes and utilize freeform geometry, an aspect that you really have to consider is your mixture design and the fundamentals of what makes a sort of a mortar mix, or what makes a 3D printable mix actually 3D printable. Now, for this, there are four very important aspects that one must consider. The first, pumpability. Can you actually pump this material without having it segregate under the high pumping-induced pressures? Secondly, extrudability. This is the ability of the physical paste to be extruded through the nozzle, so go through the pipe and then exit at your deposition point. C, buildability. Can you actually fabricate the object that you intend to create? Is it physically possible? Are you sort of transgressing the boundaries of your material's capabilities? And then finally, what is the influence of your fresh state parameters on the structural integrity of your component that you fabricated? So, addressing this fresh state material property, we utilize a property of fresh state materials called thixotropy. Now, thixotropy is essentially a material property of 3D printable mixtures, where, as you can see, you have a static yield stress and then a dynamic yield stress. So essentially, the static yield stress is if you use a rheometer, like the ICAR rheometer, which we use indicated on the screen here, to measure your resistance, you reach a certain point. You can imagine this sort of in the sense of friction. You've got a static friction coefficient and a dynamic friction coefficient. Once the static yield stress is exceeded, the material then deflocculates. And we have this, what we call a shear thinning response. I'll get into the diagram on the right now. And then we enter the dynamic yield stress. This is essentially when the material is flowing. So if we look at this figure that I have, the process diagram on the right, once the material, if it's just lying there, it's in its resting phase, it's a completely structured matrix. As you can see, you have this interconnected sort of particle shape, and then you can expect an elastic response from the material. If there's a certain load induced on it, it would sort of recover the displacement that has occurred. Now, if you apply pressure, if you shear the material, so if you take the pump and this auger turns, or you have a poker vibrator or something, you induce energy.
So you need to agitate it.
Absolutely. You agitate the structured matrix, and then one exceeds the static yield stress of the material. And then as it deflocculates, comes down on this curve, you get a shear thinning response, which is a partially structured or viscoelastic response. If you add or induce some further agitation, we reach a fully agitated phase. Now, this is what corresponds to this dynamic yield stress, the flowing yield stress of the material. This is a completely unstructured or viscous response. If one were then to leave the material, to let it stand, it then recovers this, it's sort of to its partially structured state, which is then what we call reflocculation. So you move back up this curve. If you leave it long enough, you will then once again reach your completely structured phase. So this is essentially the critical material property that we utilize to ensure that we have a concrete mixture that we can pump, but when we deposit this material, it actually has the required amount of stiffness to give you a vertical building capability. Because if you think
Yeah.
about it, this is essentially just a zero slump material that
Yeah.
we're depositing layer or contour upon contour upon contour. However, we need to be able to pump this sort of zero slump material to get it through the delivery system.
Yeah.
And this is essentially the mechanism that we utilize for 3D concrete printing
Yeah.
mixtures.
And you want to make sure that obviously that that layer of concrete that you put down, what do you call it? Do you call that like a filament,
A
or do you
filament,
call it a
yes,
bead? A
yes,
filament. Okay.
a
Similar
filament, yeah.
to 3D printing concepts.
Absolutely,
Yeah.
absolutely.
So then the filament that you lay, it needs to be stiff enough and strong enough for you to then lay another layer on top of it, and then still maintain or retain its shape at least.
Absolutely.
Can you expect a bit of a deformation when you place other layers on top of it?
Yes. So one of the critical aspects that we consider in 3D concrete printing is, can this material physically retain its own shape? So as you're
Yeah.
depositing the material and you building vertically, obviously each layer stacked upon the previous layer, each consecutive layer, then the structure needs to be able to add this aggregated weight of all the layers that has been deposited. And then if you obviously start getting free form shapes and that, you're creating eccentricity. And then we look at two material sort of yield criteria. One, which is plastic collapse. So you exceed the plastic yield stress of the material, or
Okay.
elastic buckling. Both of
Yeah.
these can occur. Now, just to get back to the mixture and how we actually create thixotropic mixtures. So I've got here an example of the mixture constituents, the mixtures that we actually use.
Yeah.
And this is the mixture that I use in my PhD. So
Okay.
as you can see, we use fine aggregates. We use cement, fly ash, microsilica fume, water, superplasticizers,
Yeah.
viscosity modifying agent, and high modulus polypropylene microfibers.
When we look
In
at that fine aggregate, is in terms of particle size, what's the biggest particle size that you normally would get in the
we
mix?
I use a maximum particle size of 4.8 millimeters, so
Okay.
quite a bit smaller than conventional concrete. So this is more of a mortar or a
Okay.
grout. However, for institutions abroad go as small as 2 millimeters. But this is essentially linked to the quality of the surface finish. The smaller and the finer your aggregates, the higher
Smooth.
quality,
Okay.
the smoother your mixture is essentially.
Okay.
So the better aesthetic appeal. However, if you sort of have to consider structural performance or aesthetics,
Yeah.
you'll have to find a balance between each of these. Now, something that's very important to create thixotropic mixtures is this decreasing particle size, or sort of your grading. We
Okay.
try and densify the microstructure as far as possible. So we use continuously graded mixtures, or the dry constituents in our mixture is continuously graded. So if you look
Okay.
at this figure that I have, you can see that all the voids that the larger particles create are filled by smaller particles.
Yeah.
And then those voids between the larger and the smaller particles have more smaller particles, or even
Okay.
smaller particles that fill those voids. Ultimately, what this does is it densifies your microstructure and allows for closer contact between the particles. So you have stronger interconnected
Mm.
particle forces. Your van der Waals forces are stronger. So then
Yeah.
you physically have this material that is able to reflocculate. This
Yeah.
reversible nature that I previously presented, being able to recover from a completely sheared or completely unstructured matrix, then
Yeah.
again to a structured matrix with an elastic response.
Mm.
And this continuously graded mixture is critical to this thixotropic characteristic that we
Yeah.
utilize.
When we
Um,
look at the microparticles that you do get, I take it because of the very fine particles, that's what now holds the shape that of the filament that you print.
Absolutely,
Okay.
absolutely.
Okay.
So, just to further elaborate
Mm.
on the importance of thixotropy and what this means for 3D concrete printing, over here, the graph that you see top left is a model developed by Dr. Jock Kruger. He's currently my co-supervisor on my PhD. And essentially, the two gradients that you see on this curve, R-thix and A-thix. R-thix refers to the rate of reflocculation, and this is these, the van der Waals forces that physically, because we've got a densified microstructure, pull towards one another. These particles physically attract one another. And this is a physical phenomenon, which is very important because this makes it reversible. We can physically have a material, structure it, and then we can deflocculate it. We can add energy and then get it into a flowable or a viscous state again, but we can reverse this. However, due to the chemical nature, calcium silica hydrate forming, so your hydration products, due to the hydration kinetics of the mixture, you have a certain chemical component to the sort of stiffening or curing of your material, which is called the rate of structuration. Now,
Okay.
physically, how this occurs is if you look at the figure at the bottom here, A, B, C, and D, you have these
Yeah.
particles that have reflocculated due to the physical forces between them. And now between those particles, we then have the cementitious particles and your pozzolans, like the silica fume and the fly ash,
Yeah.
reacting and forming their hydration components, calcium silica hydrate, and so forth, enrinite, and a whole host of byproducts, ultimately then creating this microstructure, the interconnected microstructure. However, this process is not reversible. So we have this sort of trade-off, we call it a physico-chemical response. We have a certain
Okay.
component that's physical and reversible, and a
Yeah.
certain component that is irreversible and chemical by
Yeah.
nature. So
So meaning
essentially,
meaning meaning from a how can I say a general, if I for lack of a better word, layman's point of view, is that once the cement is started setting, it's setting, and you can't reverse that. Would I be correct in my assumption?
absolutely, there's a
Okay.
certain component which you cannot reverse over the
Yeah.
longer time frame, but within the short-term time frame, there is a reversible component. So for
Okay.
3D concrete printing, and what this means to the general public is there's a certain time frame in which you can 3D concrete print, in which your
Okay.
material has before you can, within which you can deposit and actually use this material to print.
Yeah.
You can't after a day then reverse
Yeah.
this process. You have
Can
until its initial setting time.
Yeah. Can we then also say that when it comes to 3D concrete printing now, the batch that you batch up, it can only be done in certain quantities at a time. You can't just do a whole couple of cubes one time. You must obviously control the batch that you mix up for a
Yes,
specific print.
absolutely. So theoretically, you could do very large batches, but however, your quality control would suffer
Yeah.
from this. So it would once again be more of a practical consideration where you trade off the level of surety that you have as to what your material supply is versus, creating large quantities, economies of scale in this regard.
Yeah.
Um, so then just back on the topic of filament shape retention. So we have a certain portion of our material. If you imagine this filament, as you can see, there's an undeformed sort of rectilinear filament that I'm showing on the screen now. But
Okay.
when you deposit this filament, there's a certain portion that is laterally unconfined and a certain portion that is laterally confined. And what we do is we utilize this graph, the rate of reflocculation and the rate of structuration, to predict the stiffness of the material that we are utilizing,
Yeah.
um, to determine whether or not this filament would, one, be capable of carrying its own weight once it's
Yeah.
been deposited, what is the amount of strain or the flow induced, and then secondly, stacking these layers upon one another,
Yeah,
if the material is stiff enough, it would stand, as you can see on this left-hand column.
I see that.
But
Yeah,
if you
yeah,
were to exceed the stiffness or the load-bearing capacity of this material, if its own weight were to exceed, you would ultimately
get
collapse.
failure. Yeah,
You would get failure during your print. So this
yeah,
is, we utilize this figure on the left-hand side, our static yield stress evolution over time, or essentially your material resting time, to optimize our constructability, to
yeah,
ensure that we can print as fast as we possibly can, but
yeah,
ensuring that we can still create the objects. So
yeah,
obviously we then optimize our material parameters according to the components which we would like
yeah.
to produce.
And from what I can see and what I can also understand from the last presentation plus this presentation so far is that there is a timing element in terms of when you place one layer before you can place the next layer. And I take it the same graph will then tell you based on your material and materials property how soon can you then start depositing the next layer.
Absolutely. So
Okay.
essentially the loading that you induce is the own weight of the filament. So
Yeah.
you can calculate this by the density of your material times G times H, rho GH.
Yeah.
And then essentially that load corresponds to a certain shear stress. So this is sort of a rheomechanical consideration. The rheometry, the rheology of your material, fresh state property, and then the mechanical aspect to load bearing capacity. And then
Yeah.
if your material has structurated past a certain stiffness and you are inducing loading that is less, you can obviously deposit the next filament.
Yeah. Yeah, now that you mentioned rho GH, it's reminding me of my geotechnical lecturer when I was at varsity.
Yeah,
It was a famous equation
hydrostatic pressure.
he kept on drilling into us every day. We'd come into class as rho GH, rho GH. So yeah, it's
Yeah,
bringing back memories of varsity. Just
yeah.
maybe a quick question now in terms of the mix design. Is there a specific concrete strength that you work towards, or can you get varied concrete strengths? What are we looking at in terms of your concrete strength?
Yes, absolutely. So these mixes are completely customizable. As
Okay.
with normal concrete mixtures, you have a target strength which you design for, and then ultimately try and reach it.
Yeah.
However, in general, you'll see mixtures from about 25 MPa all the way up to 70 MPa due
Wow.
to these sort of more mortar or grout-like constituents that we use and the particle sizes. We have quite a lot of binder that we
Yeah.
use, very low water to cement ratios,
Yeah.
0.45, which then gives quite a lot of strength to the
Yeah.
material.
So you can keep
Uh,
it higher strengths and bigger strengths.
Absolutely. However, we appreciate the fact that you don't necessarily always want unnecessarily strong concrete. You know,
Yeah.
it should be pragmatic. It should have a intended application.
Yeah.
So you can then design mixtures for a certain target strength, as I
Yeah.
previously mentioned.
Yeah. And then just obviously, for those who use conventional concrete, when it comes to your mix design and casting on site, you normally take cubes and test the cubes to test the strength. Now, this is not your conventional concrete that you pour. How do you take cubes, or do you make your own cubes, or how do you test the strength of concrete? Maybe pocket
Yeah.
core at the end of the day.
So what we do is we print sort of sample
Okay.
objects, which we then either saw cut prisms from, or we
Okay.
core um, elements out of it and test it. So for
Yeah.
compression, we core samples because we want an aspect ratio of 2, L over
Yeah.
D of 2 to sort of adhere to your code specifications. And then for flexural samples or direct tensile samples, we then use sort of strips or ribbons that we saw out of, say, if you look at this figure on the right of my screen, you would sort of saw a piece out here and then you test it.
Yeah. And I see on the slide here, are we looking at the different modes of failure when it comes to 3D printing?
Yes. So an aspect that I sort of previously mentioned, you have your fresh state considerations, and then those with your print parameters influence the structural integrity of your 3D concrete printed component. Now, the graph over here on the left-hand side illustrates the bond strength in MPa and the printing time gap. So after how long, which duration has the next filament layer been deposited on the previous filament? And as you see, this greatly decreases with time. So at, say, this is work done by Lee et al., American institution, and they are, well, researchers from America. And as you can see, the bond strength after, say, 0 minutes between two deposited filament layers in direct tension is 2 MPa. That blue sort of arrow indicates this. But after 1 hour, this bond strength has reduced to 1.5 MPa. So this is very similar to the formation of cold joints when we cast slabs, or you know, when we sort of cast a column and then move up to the next one, we form cold joints between the material because you've had a material that's stiffened and then the next one is deposited on it. So coming back to your previous question, determining what stiffness the material must be to be able to create the object, we are also essentially racing against time to allow our material to be stiff enough so that we can quickly deposit the next layer to ensure that we have a high interlayer bond capacity, bond strength between previously deposited filaments. So for larger construction projects, we would very much have to consider after how long we've deposited the next filament. Say you print a portion of a wall or something, and now you want to carry on the next day. This is something that you would have to consider and maybe provide additional reinforcing at that location to ensure that the effect of this sort of cold joint is mitigated. So with shorter printing time gaps, we have a higher interlayer bond strength. And this obviously has one effect on the mechanical performance or the anisotropy prevalent in your mixture, and then two, on the durability of your material. If you think about it, if you have planes or interlayer regions with weakness, this would obviously compromise the durability of your structure. Shown in this figure on the right-hand side, where they poured water in the structure, and as you can see, the layers that they waited too long on to deposit,
it didn't bond.
The water is leaking through. So obviously, in terms of, you know, your chloride ingress or all your you know, your durability considerations, sort of protecting your rebar and your cover specifications should consider the printing time gap between subsequently deposited layers.
So it's a very fine line between obviously trying to get the timing right so that you can achieve, you know, the bonding between the layers, and, you know, not creating your cold joints and all of that. So I guess, you know, timing is quite key. And when it comes to now printing the structure or the element that you want to print, don't go too big. Just be, you know, I guess you just plan it out and make sure that, just to prevent, you know, these unnecessary cold joints and stuff like that.
Absolutely. That's as I mentioned in the previous time we spoke. That's why I favor modular components. This addresses you've got a lot smaller printing time gap between components, which then essentially I can optimize my time gap with my layer geometry. So sort of the path that I follow, I purposely follow a path with a shorter time gap to ensure that I have higher interlayer bonding. So these are all aspects to consider but which can be mitigated with,
Yeah.
proper consideration. It's just a design aspect, as you have
Yeah.
with general concrete construction.
And if I can just maybe just inquire as well, this being obviously a new innovative 4IR type technology, and if you look at now other aspects of 4IR, that being your artificial intelligence, machine learning, and all of that,
Yep.
I take it you can then, looking at your material properties and taking all these things into account, you could theoretically model the print and then, upfront look for these potential failures that could form and then try and mitigate them before you
Absolutely.
do the actual physical print.
Yeah, so these are actually, we've published a paper on that. It's called Benchmark
Okay.
Structures for 3D Concrete Printing. And
Okay.
in this, my colleague Frederick Bester models the fresh state properties of 3D concrete printed filaments and then predicts when these layers, when it would fail. So
Yeah.
if you're printing at too high a rate, adding material too fast, then obviously you exceed the capacity of the material in the fresh state, and then you'll have collapse. Similarly, you'll see models from Eindhoven, so the abbreviation is TUE, the Technical University of Eindhoven, where they've got a professor there, Professor SAICE, that has developed models that include both plastic collapse as well as elastic buckling. So
Interesting.
then you have a second sort of failure mode, and these
Yeah.
can be modeled in depth and studied. There's also empirical equations to
Yeah.
determine whether or not it would plastic collapse. This is
Yeah.
something you can find in the work of Dr. Job Creer, and then the elastic buckling, like I mentioned, Dr.
Yeah.
Akker Suiker from the Netherlands.
I'll definitely look for those papers and then download them and research them further. It's a
Yeah,
very interesting topic, I must say. So we spoke about now elastic buckling. I think you mentioned something about plastic failure, and we've looked
yeah.
at now this cold joints. Is there any other type of failure that you could expect?
In the fresh state, or are
Or
you?
just in general with when it comes to 3D concrete printing?
Yes, so in the fresh state, I think we've covered everything.
Yeah. Yeah.
However, in the mechanical state, due to the sort of layered structure, because we're stacking layers upon one another, we have anisotropic material behavior. So it's
Yeah.
not the same in all directions. So you require orthotropic material models to
Okay.
simulate the structural response. So in one direction, you'll have different strength.
Yeah.
The direction that is directly over the interface. So if you
Yeah.
look at the structure on the right, if you were to pull it, say, to the top of the page and to the bottom, it would be weaker than pulling it from left to right,
Yeah. I hear you.
due to the orientation of the filament layer.
Yeah.
So I wouldn't say that this is necessarily a different failure mechanism from those that you would, your normal tension, compression, or shear,
Yeah.
which you can expect in conventional concrete. However, there's a consideration as to the capacity of the component regarding those failure mechanisms.
Yeah. And I take it the things like maybe installing, reinforcing might be something that could mitigate against those other type of failures as well.
Absolutely,
Yeah.
absolutely. So this would be the same premise as you would have in conventional construction.
Yeah.
You would have a certain capacity, which you would then, concrete's weak in tension, strong in
Yeah.
compression. So
Yeah.
obviously use the concrete as your compressive resistor, and then use your rebar as your tensile resistance
Yeah.
in the components.
Look, then also at the end of the day, it all depends on application, where exactly you are planning to make use of the product or the structure.
Absolutely.
Yeah.
Absolutely. So we will definitely follow, the path that's been set out for us in conventional construction and design these components for the intended use.
Yeah. No, definitely. No, that's
Yeah,
the engineering way of doing things. You
absolutely.
design thing that's fit for purpose and for what
Yep,
it's made for. Yeah. But
absolutely.
thank you for taking us through this mixed design. It adds on to what we had discussed in our last discussion. We're just adding on, looking more in depth into specific components of it. It's like I said last time, this unique, innovative type of technology, and that us as South Africans are within our environment leading. And we will definitely look at another episode sometime soon. Perhaps something down the line of reinforcing. So I guess that will
Absolutely.
be something good to discuss about.
That'll be an interesting chat.
Thank you, Martian. I think you shared your details with us last time.
Yes.
So again, to the audience out there, thank you. I see you put your details up again. So to the audience out there, if you have any further questions regarding 3D concrete printing, you're more than welcome to drop comments down below in the video down below. So if it's on YouTube where you're watching us, on LinkedIn, any other platform where you found this video, please drop a comment down below. We'll get back to you. You've got Marshan's email address. Drop him an email. Again, we hope that you enjoyed this video. Please put a thumbs up, like the video. Again, hit the notification, subscribe, and so that you always get the latest content from us as and when we put this out. So again, thank you once again to Marshan for joining us and having this discussion. And thank you to the audience for watching.